Okay, gang, so now that we've finally handled the derivatives of carboxylic acids and we've taken a little detour through amines, now we've finally gotten to carbohydrates. Now I'm not going to lie to you, there's not a whole lot of mechanism, reaction completing type of questions associated with carbohydrates. I am going to warn you though, there's a lot of Fischer projections, a little bit of stereochemistry, and I'm not going to lie, some memorization, which if you guys know a little bit about me now, I'm all about applying concepts and looking for patterns and stuff like that. Memorization is kind of a drag, but in kind of a way, we've done a lot of big reactions with big mechanisms, with kind of big synthetic strategies going on. So in a way, some kind of brute force memorization, while it is boring, is kind of nice. So this video, I just want to kind of explain some terminology associated with carbohydrates, or I might just call them sugars, but just some terminology. I'm going to stop the video a couple times to kind of draw some stuff, erase some stuff, but I want to kind of lay a little bit of a foundation for the videos to come. And I think you'll see really what it comes down to with carbohydrates is being able to draw the structure of sugars in different forms. Okay, so just some basic terminology to start off. So the way you know you have a carbohydrate is it will kind of adhere to this type of formula, right? And if you've taken a biology class before, this might be kind of like, old hat. So what you're going to see is you'll have carbon, hydrogen, and oxygen in this kind of ratio, right? So an N will be some type of integer, right? So one carbohydrate I know we've all heard the name of is glucose. So if I choose N to be 6, right, that means we'll have 6 carbons, C6, H, not 6, but 12, right? Because this will be 2N, C6H12O6, right? And this is kind of like an infamous carbohydrate, right? Everybody knows about glucose. We eat it every day. Okay, so it's, what our bodies break down for energy. Okay, so now that that's kind of just, so yeah, like N can be any integer. 1, 2, 3, 4, whatever. So let me kind of, I'm going to erase this, I'm going to kind of gather myself, and I want to show you 2 different ways we can represent glucose. Okay, gang, so I mentioned before that we said glucose would be C6H12O6, right? This would be the molecular formula. However, when we're drawing carbohydrates, right, this doesn't really give us a huge amount of insight as to what glucose actually looks like, right? Because there are going to be chiral centers everywhere, right? There's going to be wedges, there's going to be dashes, right? Okay, so right here, sorry if it gives you a little PTSD, but Fischer projections are back, and we're going to be working with them so much, you guys will be pros at them by the end of this little series, okay? So in addition to adhering to this formula over here, right, we said CH2O, you write to some N subscript for the molecular formula of a sugar, right, we can represent them as Fischer projections, right? And when at first glance, you know you have a sugar, when you look at the Fischer projection, if up top you see this CHO, right? And if you're not comfortable looking at that, just remember, I'll kind of expand this, what that means for us, CHO, right, that's an aldehyde, right? So you have an aldehyde at the top, and then on the bottom, right, you'll see the CH2OH, which all that is, right, if I expand this, and I'm just doing this for the first time you guys see this, is an alcohol on the bottom, right? So you'll see up top this aldehyde, which I'm going to replace it back like this because no one draws it like that. You'll see CHO, that's an aldehyde, and on the bottom you'll see the C2 hydrogens and the alcohol, right, the OH. So up top CHO, on bottom CH2OH. Okay, now what do you expect to see in between the top and bottom carbons? Well, you just see, as many carbons as there are in the sugar, and you'll see a hydrogen on one side and an OH on the other. Now, right, the sugars we're going to be dealing with are going to vary between 3 and 6 carbons long, right? So here we have a 1, 2, 3, 4, 5, 6 carbon sugar, right? And what you would call that, right, because carbohydrates end in, if we're going to call them, like give them generic names, their endings come with OSE, right, like glucose. So if I wanted to generically refer to this 6 carbon sugar, I would call it a hexose. If I wanted to deal with a 5-carbon sugar, that would be a pentose, right? 4 tetrose, 3 triose, okay? Now, specifically, right, this is an, we see there's an aldehyde, right? So this is a 6-carbon aldose, right? So it's a hexose because it has 6 carbons, but because there's an aldehyde here, we call it an aldose. Now you might be thinking, okay, Joe, what else could it be? Why is it always an aldose? And the answer is no. It can be something called a ketose. So stay with me. I'm going to just basically shift the carbonyl up one spot right here. So I'm going to put CH2OH up top. I'll just draw and you guys will see what I mean. Okay. So, if you see this CHO up top and the CH2OH on bottom, this is an aldose, right? You have a sugar. Well, if you have an alcohol up top and an alcohol on the bottom, and you see a carbonyl kind of in that second position, right? It's not an aldose, right? So this is a ketone, remember? Because aldehydes are terminal, ketones are in the middle of a structure. This would be a ketose. However, right, we still have 1, 2, 3, 4, 5, 6 carbons. So this is still a hexose, right? It's a 6-carbon, it's a hexose, but more specifically a ketose, a 6-carbon ketose. A carbon name I definitely know you guys would know for this. This is glucose. This is called fructose. Okay? And don't worry, I'll get into more of what these structures are, like all the different names and all that stuff. This is kind of just like an intro. Just wanted to introduce the idea of calling things a hexose or a pentose and an aldose and a ketose, right? Okay, so ignoring this guy, because we'll mostly be working with aldoses, we can also, and I'll show you how to do this, go from a Fischer projection to our familiar flat line representations of sugars, right? This is glucose, and I'm going to tell you guys, this is also glucose. So don't worry, we're not just going to be working with Fischer projections. Okay, what I want to do is I'm going to erase this, I'm going to pause the video one more time, and I want to talk about one kind of more naming convention, and then we will move on to another video and kind of get into the nitty-gritty aspects of carbohydrates. Okay, gang, just want to tackle a few more things, and then we will close the book on this video. Okay, so, right, we're working with Fischer projections. If you need a little refresher on Fischer projections, you can go jump back to the stereochemistry series here on JoChem and get a quick little refresher, but I'll do a little mini run through right now. Remember, every time you look at a dot in the Fischer projection, remember, the side lines, they look like their arms coming out to hug you, aka they are wedges. On the flip side, the ones going up and down, they're kind of going back away from you. So they are kind of like dashes. Just as a quick reminder. I bring that up because we can assign stereochemistry to each of the stereocenters in this sugar, which I also just drew glucose again. So I'm going to assign stereochemistry once, and I'm going to show you guys a little bit of a shortcut. So if I'm going to look at this carbon right here, because this carbon has a double bond to oxygen, he's a carbonyl, he's sp2, he is not a stereocenter. This carbon on the other end is, because we're bonded to an OH, a hydrogen, this carbonyl, and then the rest of the chain down here. That is definitely 4 different groups. Okay, so if I'm going to rank my groups, right, the first atom attached to the stereocenter with the greatest the greatest atomic mass is definitely oxygen. He gets the number 1 spot. The OH is the first priority group. I would have to say this carbon up here is number 2 because although this carbon down here, right, carbon, there's a tie, he's bonded once to oxygen, this carbon has a double bond to oxygen, so he wins out. Hydrogen's obviously going to be 4th, and that group will be 3rd. Okay, now remember, it looks, right, 1, 2, 3, it looks like we're going left, it looks like it's S, but remember, this hydrogen's facing us. So what looks like S, this stereocenter, is really R. Okay, now notice You see how this is R and the OH is on the right-hand side of this sugar? When you have an aldose like this this has to be the case, with the aldehyde up top and the C2OH on bottom, whatever side the OH is on, if it's on the right-hand side, you have an R stereocenter. If this OH is on the left, it's S, right? So if I want to go through this whole sugar, glucose, right? This is R, S, R, and R. So assigning stereocenters, assigning stereochemistry on a sugar, on an aldose like this, easy. Now, just wanted to bring that up. So here, let's do another example real quick. I'll just make up a sugar. Let's do OH, 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 OH. Fill these hydrogens. Okay, so I see the COH, I see my aldehyde up top, I see my alcohol on the bottom. S, 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 R. It's that easy, guys. Okay, so I kind of want to introduce two more terms, and then we'll call it quits. Okay, so maybe you've heard, all right, so I've been telling you guys this is glucose, right? And that's absolutely true. But there's one more aspect about it I haven't been mentioning. This is what you would call D-glucose, okay? And here's why. Given this configuration, you determine D or L based on the last stereocenter in the molecule you can see. Okay, so you see how this R is on the right-hand side? Well, if that's the case, then you would designate that not only is this glucose, right? It's used D-glucose. So you might be wondering, okay, what's the opposite of D-glucose? Because you use a different designation when this OH is on the left side of your sugar. However, it's not just that. You have to take the whole enantiomer of this molecule, and I'll show you what I mean. So if I take the mirror image of this molecule, remember, two enantiomers differ stereochemistry at every stereocenter they have. So while this is R, S, R, R, the other version of glucose will be S, R, S, S. And here's what that would look like. One second while I draw this. Right, so R here, that means S over here, OH on the left side, then OH on the right side, OH on the left, OH on the left. Okay, and we can double check, right? S, R, S, S, R, S, R, R. These are this is a pair of enantiomers, right? So this is still glucose, make no mistake about that. However, instead of D-glucose, you would call this L-glucose. Okay? So D and L terminology come from looking at the last OH stereocenter and seeing if the OH is on the right-hand side, that means it's D blank, right? Insert name of sugar. Or if you have the OH on the left-hand side and it is the exact enantiomer, the mirror image of the D carbohydrate version, it would be L of that carbohydrate. So that was a lot of words. Let me erase this. Let's just do just kind of a quick another example. Okay, let's erase this. I'm not really up to date on my names of the sugars, but we'll just go through the exercise anyways, right? So let's do CHO. Draw my line, CH2OH. So you think to yourself, okay, this is some type of aldose sugar, right? And here I'm just going to draw. We'll make this a 5-carbon aldose, a pentose, right? What if we did something like this? Right? So here's what we would say, right? Configuration here, OH is on the right-hand side. This would be R, S, R. And then if we looked at the last stereocenter, the OH is on the right-hand side. So I don't know the name of this given carbohydrate, but this is the D version of it, right? A little squiggly line where the name would go, right? D blank. So what if I gave you guys the task of drawing the L version, right? Well, you still have your COH up top and your CH2OH on the bottom. Remember, this needs to be the enantiomer. So just invert every stereocenter. All right, so the OH is on the right side here. Let's put it on the left. OH should go now on the right side. And last one, OH is on the right here. Let's put it on the left. So right, you can see the mirror image of the two, right? And so this would be L, insert the name of the sugar, okay? So, like I said, guys, I'm sorry if this stuff is dry. I'll try to make it fun, but basically what we're going to be working with here is knowing the names of all these sugars. I'm going to include kind of like a layout of all of the D aldoses. You guys should have those memorized, all the 3 carbon to 6 carbon aldoses. In addition, moving forward, we're really just going to be looking on how to represent these structures using Fischer projections, how to kind of take the Fischer projection and turn it into something called a Haworth projection, a few reactions, and just basically drawing the structures. So stick with me, guys. I know this isn't the most exciting stuff, but just like every other series on GeoChem, we'll get through it together.